morning. It's my very great pleasure to introduce Ashay Ray. Ashay is a graduate student at UT Austin. He'll be talking to us about his work on side-channel defenses for microprocessors.
All right. Okay. Well, thank you for the introduction. It's a small enough room. Let's keep this interactive. Ask me questions anytime. Stop me anytime you have questions, and I can adjust the time accordingly. All right. So over the last year or so, you may have seen headlines like these about Spectre and Meltdown, which were considered to be the two most devastating bugs discovered in processors. But the reality of it is that Spectre and Meltdown are just like the tip of the iceberg. We have a much bigger problem on our hands in terms of broader side channels. And this talk is one approach as to how we can fix that problem. Okay? So by and large, private or confidential information exists in a variety of different application domains. And across all of these domains, our goal is to make sure that that information remains private. Or in other words, we want to prevent the leakage of that information. And along those lines, there have been several techniques that are deployed and are actively used, like encryption to scramble that information. There are techniques like authentication, authorization, perhaps even multi-factor authentication to limit the entities that have access to that information. And there are also techniques like virtual machines to mutually isolate the attacker from the victim. And the frustrating part about all of this is that even if you were to use all of these techniques together, it is still not sufficient to prevent leakage through what are known as side channels. Now, I think most of you are familiar with the term side channels, but just to make that a little more concrete, let's say you have a sensitive document like a bank statement, and all that you want to do is just open that document and read it. You want to read the contents, but of course you don't want the contents to be leaked to an adversary, which could be a concurrently running application on the same machine, or it could be some other user who is logged into the same machine as well. Now, the thing that is relevant over here is that the task of actually displaying those characters on the screen is actually a fascinatingly intricate and complex process, starting with a single letter. So something like O, when it needs to be rendered on the screen, it needs to be drawn using a set of lines and curves. So there are 4 curves for the inner ring, 4 curves for the outer ring. But now if you were to take a different character, like A, there are a lot more curves than there are straight lines. And for something like V, there are a lot more straight lines than there are curves. And in fact, on a side note, like modern typography is so fascinating in the sense that you have features like ligatures, where you have combined characters being drawn in a specific way, or you have kerning, where you adjust the spacing between characters based on the characters themselves and so on. So you might be wondering, why is this relevant? The reason why this is relevant is because the amount of time that it takes to draw each character is actually directly dependent on the character itself. So letters like I or the digit 1 have a fairly short rendering time, as opposed to the digit 6, for instance, which has a lot more curves. And you can actually try this out on your own machines as well. In fact, just last night I was putting together a quick proof of concept where this is on a somewhat simulated setup where there's this original text which is being drawn into a bitmap file. And this is the victim portion of the code. And the attacker portion is trying to guess the character that is being rendered based on the amount of time that it took to render that character. And it comes up with something like this, which is, of course, not a perfect rendition of the original text, but it is actually surprisingly effective. It got 41 out of those 52 characters correct. And most importantly, it got most of the numbers right. And you can further improve the accuracy of this by using a dictionary, by using Markov models, or any kind of prediction on top of it. But the broader point is that the attacker can measure the execution time of the application to infer sensitive information about the program that is in the program. And this is hard enough to make sure that the execution time does not leak information, but that's not the only side channel, so to speak. In fact, 4 years ago, Marcus Minardo here at Microsoft Research, along with a few others, had demonstrated this on. Were you there as well, Vedang, on that paper? Oh, okay, sorry, my bad. But yeah, so this is exactly the case as well, where you have a text document being converted into a bitmap, and to make sure that the document is not leaking information directly through memory, the document's memory is not visible to, say, concurrently running applications. It is being run inside an SGX-like enclave. This is like a sandbox mechanism. The problem here is that in this case, it's not the execution time, but the attacker is measuring page faults or is observing page faults. And it's the operating system which is malicious. And just by observing those page faults, it is able to reconstruct the document contents in its entirety. It's a slight variant called a control channel attack, where the attacker, the operating system, is inducing page faults and is observing them as they go along. Which in some sense is not surprising, given that the memory address trace of this entire rendering process is also relevant or based on the characters themselves. So for something like X, Y, and Z, the horizontal axis shows time in terms of different memory accesses. The vertical axis is showing memory locations. And for each character X, Y, and Z, you have a different footprint. So if the attacker could intercept your memory accesses, like in the case of page faults, for instance, then they can infer your document contents. And the same case holds for the execution trace as well. So this is the trace of basic blocks, or the sequences of instructions that were executed. Now, as it turns out, these are not isolated cases. There are a whole slew of different side channels at different layers of the computing stack, which all leak very similar information, ranging from your caches, your page faults, your address trace, and so on. And so what that effectively means is that if any of these side channels are visible to your adversary, then your document contents can be in jeopardy. Now, this is actually a hard problem to solve. And before I talk about how my solutions essentially close these different side channels, I want to give you a flavor of why this is a hard problem, and why is it that some of the people who have tried to solve this before us have, I think, not been able to hit the nail on its head. Okay? So if you step back and think, what is the core vulnerability? And if you step through the execution of the code, you'll notice that for different characters that are being drawn, the code actually executes different paths. For the letter A, it goes down one path. For letter B, it has a slight deviation from the original path, and so on. And because you have these differences in the execution paths, you are, of course, going to see differences in the execution time, in the cache behavior, in the TLB behavior, memory address trace, and so on. But that realization that many of these side channels are caused because of specific variations in the source level behavior is often missed by prior work. And so prior work often focuses, sorry, did you have a question?
I do have. What's
Yeah.
the node in this graph?
This is the control flow graph. So
What's the node here?
it's a basic block
A basic block of what? Code?
of code instructions.
So the code, the basic block of, is that constant? Like, how do you know that somehow that unit has to have no side channel attacks?
Right. So
So that's my question. What is that node? What is that node? Because it can be a block of code, because a block of code, as you pointed out, can have all sorts of weird behavior.
right. And I'm starting it from a top-down perspective. I'll talk about how we can get to within a basic block and eliminate side channels within those basic blocks. But this is starting at a very broad level, where we'll first address the side channels that arise as a result of these control flow graphs and these different.
But I should think, when I look at this graph, I should think that the nodes there are constant. There is no distinction between one node to another node from another node, right?
Other than different instructions. This is essentially the control flow graph. So you start with, let's say, the first instruction in the program, and then based on the conditional branch, you go down one path or a different path. And so each node is basically a different basic block. I'll talk about how we can close the side channels at the control flow graph level, and then I'll zoom into each basic block and address those. All right. So as a result, if you look at the prior work in terms of closing different side channels, it often focuses on these individual symptoms of the problem. So there are separate solutions for closing, let's say, the execution time side channel, separate solutions for page faults, for caches, for branch predictors, for DRAM addresses, and so on. And so a lot of these prior solutions end up being point solutions, because they're focused on individual side channels at a time. And there are three main drawbacks with these point solutions. The first of which is that, like I said, they're focused on the symptoms. So for every side channel, these solutions are constructing a completely independent solution for that specific side channel, and that's a lot of work. But more broadly, you could say that, okay, we have these different point solutions. Why not just put all of them together to get a comprehensive defense? And that becomes hard, because it can be difficult to ensure the end-to-end guarantees of that of those defenses. So because you might have one solution which might actually negate or make it difficult to argue about the security of a complementary solution which is used at the same time. And so ensuring the total guarantees can be difficult when you have these point solutions. And as another drop, yeah.
Can you give us an example of that?
I don't have that, but I can give you a quick verbal example. So there are certain cache side channel defenses which talk about randomization of fetching addresses randomly or issuing address. So in addition to servicing the specific request from the cache, but they also evict some cache lines randomly and fill them into the cache. But you could have, there are other defenses for, let's say, the DRAM address trace defense. There's one specific one called memory trace obliviousness, where the idea is that the security guarantees only apply if you have a predictable stream of references or requests that are coming in out of the cache. And so now you have, it's kind of like there's no clear specification for, or the post conditions of one defense, for instance, don't cleanly match with the preconditions for a complementary defense, and so it's hard to argue. Okay, and there are other examples I can talk about.
It's not that they necessarily conflict with each other, but it's very hard to combine the guarantees.
So that is one case where it is hard to combine those guarantees, but there are other cases. And another example could be you have, let's say, a branch, and you have two different executions or paths that arise out of it, and you want to make sure that the instruction count does not leak information. And you could make sure that you could pad it by using NOP instructions. But if you do that, now your execution delays could be different, the execution time. And so you might, now you can get like a GCD, a greatest common divisor, and then, or least common multiple, I'm sorry. But you can do that, but it quickly starts getting hairy then. Okay. All right, so the third main drawback is that many times when you're using these point solutions, you may often be forced to disable optimizations in the compiler and the microarchitecture. And here's an example of that to illustrate that. So this is a system called Ghost Rider, which was presented in 2015. It actually is a very well thought out solution. It won the best paper award as well at ASPLOS, but it has some serious drawbacks. So given a program like this on the left, where depending on the value of secret, you either issue 2 load instructions or 1 load instruction, the adversary can count the number of load instructions at runtime and infer the value of secret. So one of the things that Ghost Rider does is to add a dummy load instruction along the else path. And so now you have 2 load instructions along both cases, and so the adversary cannot get to know what is the value of secret. The problem here is that if you use any optimizing compiler, it will recognize that this is a dummy load, it is not used anywhere in the program, and it will remove it. And you're back to square one. And so more broadly, your optimizing compilers can actually break security guarantees, and so you have to disable them. So you might say, okay, let's compile with O0, let's go straight to the hardware and execute the program as it is. But even the hardware optimizations can get in the way. Like you might see cache hits for your regular addresses, but because let's say your dummy address is randomly generated, you see a cache miss over there. And so the adversary's view in terms of side channels can again differ based on your cache hits and misses. And so that can leak information. So your caches and prefetchers also need to be disabled. And so what that effectively means is that you not just end up disabling optimizations and paying the high performance cost, but you also have to redesign the processor for that specific side channel. And when you're talking about redesigning the processor, you're talking about fabrication, verification, and all these kinds of really high costs. So this is the kind of performance overhead that you see if you were to compare, let's say, with respect to an optimized Intel processor with O3, or with O3 optimizations in the compiler, but also out-of-order execution, branch prediction, variable latency instructions, and so on, because all of those need to be disabled in a solution like Ghost Rider. And so this is just to give you an idea of the kind of space that we're operating in. Okay. So just to quickly summarize, the key drawbacks with prior solutions are that A, many of these are point solutions. They're focused on the symptoms of the problem. Secondly, many of them require disabling optimizations in the compiler and the microarchitecture, and that means you have to pay this fundamental cost of hardware redesign. And third, they are often rigid in the sense that they cannot be tailored to specific parts of the application. And so in contrast, I'm going to show you our solution, which A closes a broad class of side channels, and I'll define what I mean by broad class in just a minute. In addition to closing these broad class of side channels, our solution also executes on commodity microprocessors, like those conforming to ARM v7, ARM v8, and x64 architectures. And we're also able to protect a broader class of applications, or more diverse set of applications, compared to prior work, much of which focuses on small cryptographic kernels, the broad majority of which focuses on small cryptographic kernels. Okay? So in terms of more concrete contributions, my work is broadly in the area of the compiler. So it takes in programs which may leak information through specific side channels and transforms them so that the transformed program is functionally equivalent to that original program. But the transformed program does not leak information through specific side channels. Now, these compilers are not fully automated. It takes a tiny amount of hints from the programmer in terms of annotations, and I'll clarify what those annotations are. And as you can imagine, these side channels are a property of the underlying execution. So we do have to analyze the underlying layers, specifically the ISA, the microarchitecture, and even properties of the physical hardware to be able to know that, hey, to be able to tell the compiler that this specific instruction is leaky, and so work around it so that you don't leak information through side channels. Now, this is, of course, in terms of the whole compiler, but in fact, when I was interning over here, I was working on developing a verified leakage analyzer. So this essentially takes in a program and takes in a certain model, a microarchitectural model of side channels, and tells you whether the program may leak information or not, whether it is safe or not. But the key point over here is that this is a verified analyzer. So we prove its soundness using a proof assistant, basically using the Daphne program verifier. So by the way, in addition to that, I've worked on having a similar leakage analyzer for the physical hardware, where I was looking at Verilog and analyzing whether the Verilog implementation may leak information or not. But that's not a verified analyzer, though. So at a high level, the specific work is spread across 4 different projects, the first 2 of which were focused on closing digital side channels. So these are side channels that carry information over discrete bits. So that includes the cache, the instruction count, the TLB, the branch predictor, address trace, and so on. The subsequent work, which was Whale, which was a result of the internship over here, the broader idea over there was to verify high-performance cryptographic assembly code, but my specific contribution, including, with Srinath's help, was to develop the verified leakage analyzer. And in the subsequent work called Vantage, which is still a work in progress, we're essentially taking the idea of closing digital side channels and extending it to non-digital side channels, like power consumption. And in some sense, we're trying to get to our true vision of what we want compilers to be able to do in terms of being retargetable to different architectures and customizable to handle different threat models. And so that's sort of, here's the broad outline of what I'll be talking about. I'll first describe the key ideas behind our solution, and I'll describe them using a few specific examples. And then I'll pop up a few levels to talk about what are the core principles that we use in our solution to be able to adapt or generalize to other side channels as well. I'll compare the performance of our solution with prior work, and then I'll conclude with future work in this area and outside of side channels as well. Okay. All right, so the key insight that enables us to close these broad class of side channels is that a majority of these side channels arise because of variations in the source level behavior of the program. So to give you an example, the branch predictor side channel is caused because of variations in the program path. Your memory address trace side channel is caused because of variable accesses or pointer dereferences in the program. And of course, this is not saying that all side channels are caused by that, and that goes back to your question as to within a basic block, what are the different kinds of side channels. And I'll talk about those after I talk about how we close these broad class of side channels first. Okay. So if these different side channels are caused by variations in the source level behavior, we can sort of walk up that chain and ask ourselves, okay, what causes variations in the source level behavior? And from a compiler's perspective, you can express these differences in the program behavior in terms of control flows and data flows, which themselves are varying because of the sensitive information in the program. And so the key idea that we're using in our solution is that if we want to close a broad class of these different side channels, then we need to make the control flows and data flows independent of the sensitive information in the program. And just for reference, a lot of these point solutions are operating at the bottommost space where you're addressing each side channel independently, whereas we're trying to tackle this problem at its root cause level as to how can we broadly close these side channels using a single solution. And the way we do it is conceptually by executing all paths in the program. So given a program like this, where depending on the value of the secret bit, you execute either one statement or a different statement, we force the execution of both the then path as well as the else path. And so the adversary's view in terms of side channels is always the same, no matter what is the precise value of secret in the program. And the way we do it is by using predication. So given that program, we first compute the branch predicate, and then attach the predicate P to the then part, and the predicate not P to the else part. And so that allows us to basically execute the entire program, but still get correct results by deferring the problem of writing the correct results over to the predication logic, so to speak. And the way we implement predication, at a high level, we basically need this kind of a block which takes in the old value of a memory location and the new value, and it also takes in a condition, and the output of this is either equal to the new value if the condition is true, or the old value if the condition is false. And so this allows us, given a certain predicated operation, we can either decide to write the new value or read the old value and write the old value back into the location. And the way we implement this is by using these 4 lines of assembly code. If you're familiar with x86 assembly, the key instruction is that third one called conditional move. Now, of course, conditional move does not necessarily exist on all ISAs, but we can mimic its effects by using bitwise arithmetic. And so we have similar implementations of this block of 4 instructions for ARM v8, ARM v7, and also for RISC-V as well. But given this, the key points to note about these 4 lines of assembly are that A, it has no control flow. It has a straight sequence of instructions executed one after the other. All of the data is in registers, so there are no pointer dereferences, and so there are no memory accesses per se. And third, it executes in a fixed amount of time, which we validate empirically, or which we validate using microarchitectural models, like the GEM5 model, for instance, and also empirically on actual processors by running the program multiple times. Do you have a question? Sure, yeah.
So why do you write the old value? Is that necessary to close the side channel?
The old value is just so that the adversary's view in terms of whether or which writes happened or not is independent of the secrets. So the adversary has to.
I thought, maybe I'm wrong, that the CMOV intuitively acted like a write in that it updates the cache line and it updates the bit in the PTA. Am I wrong about that?
So in this case, I'm using just registers. So I am not deferring to memory. All of the data. Yes, yeah. Because I mean.
You have the cache slide effect.
Sorry, what?
Then I don't understand why you need them all.
So it's kind of like the predication of how it is implemented in ARM processors, for instance. If you have a condition where you first preemptively write one value, and then based on the condition code, you write the new value back. And I'm doing similar operations, but doing those in registers instead of operating those in memory.
Yeah, no, I understand that, but presuppose that the output register was already at the old value. Maybe that's what I'm assuming and is not true. Then if you left off that first null.
Yeah, if I list off.
The adversary know.
Yes, so yeah, if the first instruction is not there, then you could just write the new value back. And so, yeah, I guess what you're saying is that instead of having 4 instruction sequences, you could have a 3 instruction sequence where you don't have the original, the first instruction in there, where you're redundantly writing the old value back into the output, right? Yes, absolutely, yeah. Yeah, it's functionally equivalent. It can be compressed into 3 instructions as well.
Okay.
Yeah.
And why do you need to use the flags at the end?
This is because this is sort of a conservative step, because you may have, for instance, a library function call, and the library function call shouldn't have access to the results of the comparison from this conditional move operation.
Oh, okay. So some sort of funny you haven't talked exactly about what the threat model is.
Yeah,
Yes.
Well, the security model.
Right, yeah, sorry. So yeah, I'm assuming that all of the registers are, well, I mean, any secrets in registers that go in should be cleared out at the end, and so that includes the flag registers as well. Just the results of the comparison should not be leaked to any other program.
Well, but you didn't clear other registers. Why do you have to keep clear the flag?
Oh yeah, yeah. I guess yeah. Yeah. So there is. I'm not. There could be secrets outside of those flag registers in other cases as well. Yeah, you're right. So in which case, we should either clear all registers. Yeah, I understand.
I think you should
Yeah.
pump that. That's a
Yeah.
high-level abstraction. That's like a basic block or function boundary.
Yes. Yeah. You're right. Okay. Any other questions before I proceed? Okay. So. So given this, we can now rewrite our original snippet of code so that we first save the branch predicate, and then we evaluate both the then path as well as the else path. And if subsequently, if the predicate P is true, we write the result of the execution of the then path, which is Z1, into the destination Z. Otherwise, the existing value of Z is written back into itself. Or subsequently, if the predicate P is false, then Z2 is written into Z. Otherwise, the existing value of Z is written back into itself. And I guess, I mean, you can further optimize this by just having one predicated write operation, but that's just for the sake of simplicity that I'm showing two operations over here. All right, so this makes sure that you can execute all parts of the program and get the correct result, but you can still face problems. Your program can actually crash, like in this case, where depending on the value of secret, you are assigning a value constant, or you are assigning a constant to a variable v and then performing division. And over here, the naive way to transform this would be like this, but the second line is the culprit over here. Because if the secret is false, then the existing value of v, which is 0, is written back into itself. And then subsequently, when you perform the division, you perform a division by 0, and that crashes the program. But what's interesting is that the program crashes only when secret is false. If secret were to be true, then it would perform division by 10, and then the program would proceed just as normal. And so whether or not the program crashed reveals the value of secret. And so the broad idea that is used in our solution for these kinds of cases is to actually mask these exceptions. So given a program like this, we actually surreptitiously change the value of the divisor or the denominator from a 0 value to a non-zero value. And of course, there's an underlying assumption over here, which is that the original program before transformation does not throw exceptions, but that is something that can be handled using orthogonal debugging techniques. So given a program which is not itself throwing exceptions, we are making sure that any transformation that is done by the program itself does not cause or introduce new exceptions into the execution, and that's the reason for masking those exceptions. Now, division by 0 is just one example, but there can be other architectural exceptions as well. But I'll be happy to talk about it offline if there's interest. Yes?
But how do you differentiate? Here, this solution, this is different from masking the exception, right?
No, in this case, I'm changing the divisor from a 0
so you won't have exception.
I won't have exception.
But the right one actually,
Sorry.
Right, but my question is that
Mm-hmm.
when you say you mask exception, that means you capture all the exceptions and drop them quietly?
So these are architectural exceptions, yes. So like integer overflows or division by 0, yeah.
That's dangerous in the sense that the original program may have exceptions, because we know programs are buggy.
Which is exactly why that assumption. So we're assuming that the original program is not buggy and that it does not throw exceptions.
But that assumption is never true, right? No?
It's-
Don't get it.
I mean-
his point is that he should not introduce exceptions that wouldn't have happened in the original.
Yes. So if
How do you mask
But your
exception? Do you mask
behavior
exception
will
for the
change.
whole program?
Yeah.
I mask exceptions for the whole program, yes.
Yeah, so then your concern is still
No, but hang on. When
What?
you say you mask exceptions, do you mean you do something at runtime to make sure the exception is not raised?
No.
When you rewrite the program, you make sure that you cannot.
Yes, I rewrite so that it's statically rewritten so that the transform program can never throw exceptions.
Oh, okay.
It's not, I mean, at runtime, for instance, if I were to check if an exception occurred and then mask it, then that itself would leak information.
Mask, that's,
Assuming that all pointers in the original program were valid.
Yes.
Every memory access in the rewritten program is valid.
Yes, that's right.
okay. But that's not mask.
That's not masking.
Okay.
You were saying you mask an exception.
Okay.
You didn't. You, yeah.
Right, yeah. Okay. All right, so there is one final case where predication can throw problems, and that is in the case of loops. So if you have a loop like this, the naive way to do it would be to change this conditional branch into an unconditional branch. But if you do that, then you're stuck in a loop forever. And so loops require a slightly different kind of transformation. And I'll illustrate the broad idea using this example. So let's say you have a loop which goes from 0 to n, and n is secret. We don't want to reveal the number of iterations that were executed by the program. And so the key idea that is used in our solution is to not just execute n iterations, but also execute some dummy iterations after that. And that can raise all sorts of questions like how many dummy iterations to execute, how to execute them without crashing the program or without producing incorrect results. And I'll show those using the specific transformation steps. So the first step is to generate a new loop with some new loop trip count C. And I'll talk about how we get to C in just a minute. But the second step, and the most important step, because everything else follows from here, is to take the original loop body and attach a predicate before we insert it into the new loop body. And so that allows us to control the side effects of those statements in the new loop. And we want to make sure that the first n iterations work as expected. And so we initialize the predicate true to be outside of the loop, or predicate true outside the loop. And then subsequently, we want to make sure that after executing n iterations, we want to turn the predicate off so that we can continue executing dummy iterations. But we don't want to reveal the fact that we turned the predicate off. And so we need to predicate the predicate assignment itself. And so this makes sure that we can smoothly transition from the actual iterations to the dummy iterations. There's one final part remaining as to how do we get to the value of C. And that's actually directly analogous to the halting problem. Like, there's no program analysis that can identify the precise number of steps that the program has to take to reach successful completion. And so in this case, we actually default to the programmer in terms of the annotations that I talked about earlier. But the key point is that the programmer does not have to precisely identify the iteration count, because we can execute dummy iterations. So as long as the programmer specified annotation is actually longer or larger than any real value, we're fine, because we can continue executing iterations as dummy iterations after that. Right?
What happens if it's not?
Then you get incorrect results. Like, as in, so your question is,
terminate the loop early, or do you throw up your hands? What do you do?
so if the program actually terminates. So since this is a new loop with a fixed iteration count, if that iteration count happens to be lower than the actual number of iterations that should have been executed, then it does continue, but then it will produce the incorrect result.
It sounds like panicking and dying would be a better answer.
But we don't know what is the actual iteration.
You have a
If you fall off the end of the loop at
But
runtime,
this, I mean, in some sense, this is assuming that this is there's a certain loop induction variable, and we know precisely the number of iterations. The condition for termination might not be the precise iteration count may not be known. It could be something like when some.
No, I understand. What I'm trying to say is, let's say the loop is loop until the user presses Y.
Okay.
And
Yeah.
the user never presses Y.
Uh-huh.
Having one program that blew up with an assertion failure and just stopped execution there
Yeah.
would be better than having one that just kept running with an incorrect result.
But if it's going to keep running,
That's what
then
if I understood correctly, let's say it's 1024, you'll execute the loop 1024 times.
yes.
And then you'll pull out of the end of the loop and keep going with incorrect state.
Right. Okay. So you're saying okay
If you get to 1024,
right.
die.
Okay, yeah. So we can add an assertion failure at the end, or assertion at the end of the loop, to find out whether the termination condition was reached or not, and accordingly signal to the user. Yeah, you're right.
But if that's the case, then by extension, I don't even have to ask the user for the C value. I can just make one up and see if I'm right? And then make one up again.
Well, you need
No,
to
but-
kind of use it because there's a performance and a correctness trade-off there.
But
I mean-
about correctness. Performance might
Well,
be
correctness, the program will crash if you guess wrong.
No, if you guess wrong, you keep the count down the road. You go back. I mean,
No, but then your final iteration count can change then, because in one case your correct iteration count might be small. In the other case, your correct iteration count could be large. And so if you just keep,
You're right.
you don't know how many times you have to kick the can ahead before you terminate. All right. Okay. So
but if you
yeah.
crash, but then if you put this crash or not crash, you can leave something out.
Yes. At that point, I think the program is incorrect enough that that's an acceptable outcome.
Yeah, probably wouldn't make this proof go through.
Yeah. Okay. So so that makes sure that control flows do not leak information, but there can be leakages through data flows as well. And here's an example. So in this case, you're indexing into a table based on a secret value. And the way this gets lowered into assembly is that you first have, you compute the address by adding the base address of the table to the secret and then dereference that address. Now, if the adversary had access to the final address, then they can, and the base address of the table, then they can do mere subtraction and get the value of secret. And so there are two broad solutions that are two broad options that are offered by our solution in these kinds of cases. The first is this rather dumb approach of accessing the entire array and fetching the element that you actually, or using the element that you actually wanted to fetch in the first place. That's clearly expensive, and I mean, it works well for small enough array sizes, especially given caches and prefetchers. But for that asymptotic case, when your array sizes are large, we implement a software version of oblivious RAM or ORAM. If you're not familiar with ORAM, it's essentially a construct that continuously shuffles and encrypts memory upon every access to hide the specific location that you wanted to access. But the key point is that typically oblivious RAM is implemented in microcontrollers, but we can do it in software on commodity processors by using the predication logic and the loops that I showed you earlier. And so that takes care of control flows and data flows. But now going to your question, there could be leakages outside of control flows and data flows as well. And I'll give a couple of examples of this. One is the integer division instruction. So in this case, in this plot, what you're seeing is the horizontal axis shows the location of the most significant bit of the numerator, and the vertical axis shows the location of the most significant bit of the denominator. And the different colors indicate latency of that operation. So the amount of time that it takes to execute division depends on the numerator and the denominator. Okay? So the first question is, how do you even know that this sort of a leakage exists? And the way we do it is by actually analyzing the underlying layers. So we start with the lowermost layer of the microarchitecture and ask, okay, what are the different things that affect or can change the value of the cycle count at runtime? And so there are a lot of things that come up, but one among them is the division macro operation. And then we trace the code back to say what triggers the division macro operation, and that's the idiv instruction on x64, for instance. And then we analyze the compiler backend, the code generator of LLVM, to find out that it is the sdiv, udiv, srem, and urem instructions from LLVM IR that get translated to the LLVM to the division instruction. And so for those kinds of cases, our broad solution is to basically rewrite the division operation, but without using the division instruction itself. We're basically using the long division approach, but doing it in bitwise arithmetic, and that way we can rewrite that operation without using division. But here's a more interesting case, and this is comparison. And comparison operations can actually leak information through the power consumption as well. So on the left-hand side, you see a fragment of C program where you're just comparing the result with some constant values like 3. And on the right-hand side is the way it is typically lowered into assembly. This is using 32-bit ARM as the ISA. I'll just quickly walk you through it. So the first instruction compares the source value to the constant 3, and the results are stored in the flag registers. The second instruction preemptively writes 0 into the destination. And the third instruction conditionally, based on the results of the previous comparison, writes 1 into the destination. And the key point over here is that 2-letter suffix, the not equal suffix, because the reason why this is important is because at runtime, based on the value of the previous comparison, it conditionally writes the register operations, which in turn affects the power consumption of the processor. And the other interesting point is that the number of cycles that are taken by this program are always the same, no matter the result of the comparison, but the power consumption differs. And for detecting these kinds of cases, we can do the usual analysis of the compiler backend, the microarchitecture, or the ISA as well. But for that last link, we analyze the underlying power model. So these power models basically characterize the link between microarchitectural events like cache hits, misses, or instructions executed, and the power consumption of the processor. Now, power consumption or power models can be kind of tricky to analyze because they can either be open source like McPad or
So are you saying the C move happens or not to change the power consumption?
In case of the ARM processor, the condition code does affect the power consumption. Yeah. So we didn't notice the same behavior for conditional moves on x64, but we did notice that on ARM processors then. Okay. All right. So analyzing these power models can be tricky because they can be open source or they can be closed source. So for open source power models, where we know precisely what are the inputs and outputs which are used to derive the power consumption, we can basically use a standard data flow analysis technique called backward slicing, where the main idea is that you're given a specific value in the program and you're trying to find out what other values does this specific value depend on. And so you're trying to trace your execution back through the entire code. But for closed source power models like RAPL, you don't have the precise definition. And in this case, we actually fit a regression model onto that closed source power model and use only those inputs to that regression model which have non-zero coefficients, which is sort of a hand-wavy approach, but that is the best that we can do given that there is no actual open source definition of the power model in that case. But once you have this sort of a link as to what instructions leak power consumption, the next step is to rewrite the program. And that is where we're actually using super optimizers. So given the original program where we wanted to do the comparison, we can now rewrite the program and basically use existing techniques from super optimization to rewrite the program, but rewrite them in such a way that they do not leak information through these power consumption, through specific side channels. And so here I started with this example where I was comparing source and 3, but we can do that for arbitrary operands as well. So all of this may seem like these specific transformations were like hand customized and completely independent, but there are actually some core principles that enable us to generalize and to adapt our solution to different side channels. So at a high level, we're essentially clarifying the link between the compiler or the LLVM instructions down to the side channels. So that when the compiler notices that, hey, there's a division instruction, it knows that the numerator and the denominator could be leaked through, let's say, the timing side channel. And so at a high level, we are basically creating this sort of an abstraction alpha going from the compiler down to the side channels. And we create this separate abstraction alpha for every side channel. We derive this abstraction by analyzing the underlying layers, specifically the ISA, the microarchitecture, and properties of the physical hardware as well. And if you're familiar with the term, we're essentially using taint tracking or information flow analysis to be able to derive this abstraction. The same analysis is applied to both, but given that the ISA definitions are small enough, we can do them in an automated manner. But given the code structure of the Gem5 microarchitectural simulator, we are not able to automatically apply this to the simulator. Yeah.
Question. So here, when you derive this alpha, do you derive it for every single
instruction?
What granularity of generational ISAs, or is it? So if I think about a processor, is it for every generation of that processor I have to be derived an alpha? Is it?
So yeah.
For every unit of the processor, for every different instance of the processor, what?
In some sense, side channels are directly they're an artifact of the underlying implementation. So whenever the implementation changes, you would have to redo the analysis. So in case of the ISA, given that the ISA is more or less constant, you may not have to analyze it as many times. But for each new, stepping of the processor, for instance, you would have to do this analysis all over again. Okay. All right, so the key point here is that this abstraction alpha is defined for every specific LLVM instruction. So if we were to be given, let's say, some arbitrary computation f that we want to protect, so this f takes in some inputs and produces some outputs, we can successively apply alpha to every instruction within f and compute a new function, let's call it a leakage function, that takes in the same inputs as f, but instead of producing the outputs, it now tells us a little bit about the side channel leakage when the function f takes in a certain specific set of inputs. And so the adversary is basically observing these side channels and trying to infer what is the corresponding input, whereas our goal is to make sure that despite these side channels, despite the existence of these side channels, we don't reveal the input value to that function. And so a naive way to so given some secret value x, for instance, and we want to evaluate f on that specific secret input, a naive way to hide that is to basically evaluate f on all possible inputs I. So if we do that, the adversary's view in terms of side channels is always the same because you're executing f on all possible inputs. You just pick the desired output that you wanted. But of course, this is clearly expensive, and if your space of inputs is large, then this is not tractable. And so there is a slightly better approach that is possible oftentimes, and that relies on this observation that if you look at the space of inputs and the space of different side channel observations, there is oftentimes a many-to-one relationship. Or in other words, there are a few set of inputs for which the side channel trace or the observation is exactly the same. And so if this sort of a situation exists, you can now partition your set of inputs and just use one representative input from each partition so that instead of evaluating f on all possible inputs, you now evaluate it only on one input from each partition. And that makes sure that the adversary's view, again, is consistent or is independent of the specific inputs that you want to run. And just to represent that in set notation, that's something like this. But there may be an even better option possible, and that relies on the ability to transform this given function f into a new function f prime, so that the leakage characteristics of f prime are that no matter what input you use to f, or no matter what inputs you pass to f prime, the side channel observation is always the same. And so if you can derive that, and this is what we do, let's say, with the division case or with the comparison case, and if you can derive this, then you can basically, all you have to do is just replace that existing function f with a new function f prime, and you don't have to evaluate f multiple times. But the key point to note over here is that all of the examples that I showed you earlier, all of the transformations that I showed you earlier, are mere examples of these three different cases. And so I'll come back to this idea very briefly towards the end as well as to how we can synthesize or automate the generation of our compiler transformations using these sorts of ideas. Okay, so using these ideas, we are able to close a broader class of applications compared to prior work. So that includes digital side channels and also some non-digital side channels based on whether the power model is supplied to the compiler and based on the level of detail that is modeled in the underlying power model. Our solution also executes on modern microprocessors. Basically, these are Gem 5 implementations of x64 ARMv7 and ARMv8 processors. And compared to prior work, a majority of which evaluates on small cryptographic kernels, we're able to protect a broader class of applications. Okay. Now, earlier I showed you this system called Ghost Rider, which had to trade off different optimizations, which had to turn off different optimizations for security. If you compare Ghost Rider's overhead with respect to our overhead, it looks a little bit like this. So now, our solution's overheads are not zero. There is still some cost. But the key point is that this is just the evaluation on specific Ghost Rider benchmarks. If you were to instead evaluate Ghost Rider on a much broader class of applications, then its ability to protect these applications is quite limited. And that happens because these programs often use complex control flow, or they use floating point arithmetic, and so on. Now, Ghost Rider is a shared compiler hardware solution. And so you might think that instead of trying to parse these kinds of constructs in the compiler, let's build all of our solutions directly in the hardware. And so that way, no matter what program you run on the processor, it will always be protected because your solutions are always built into the hardware itself. But if you do that, then your overheads actually shoot through the roof. And that happens because you lose contextual information about the application. And so you have to make the conservative assumption that everything could be potentially secret, and so that increases your overheads. Now, in our solution, we're able to leverage common optimizations in commodity processors like caches and prefetchers and branch predictors, for instance. But we're also able to target specific portions of the code by leveraging the compiler. And so in our case, the solution's overheads actually are substantially lower compared to prior work. And building things into the compiler not just makes it configurable, but we can also adapt our solution to the specific threat model that may be of interest. So instead of closing all digital side channels, for instance, if you had some orthogonal defenses and if you just wanted to close, let's say, the timing side channel, then the overheads are even lower. And a similar case holds for the microarchitectural power side channels, like I described earlier with the comparison operations. So all of this talks about the work that I've done, but going forward, there are certain things. Oh, yeah, sorry.
The graph of the all side channels, that includes using ORAM?
This does include using ORAM, yes. Yeah, so which is why for something like binary search, where you're, if you go down one path or a different path, you don't want to leak which part of the array you're accessing. And so in this case, it is using streaming. It is not using software ORAM. But yeah, if you were to use software ORAM, your overheads would probably be even higher. So there is this tricky case with ORAM. There is a certain threshold. There's a break-even point where if you use standard streaming, then you can get benefits with caches and prefetchers. But beyond that point, it's too difficult or it's too slow to access the entire array, and so we can switch to ORAM. But sort of the interesting point is that for larger applications like SVM, for instance, or motion tracking, the criticality of the code, for instance, is quite small in the sense that there are certain parts of the application which don't or there are limited parts of the application which require transformation, whereas a bulk of the application is something that can proceed just as normal with its usual speed. And so for smaller applications like binary search, for instance, you have this terrible overhead, but then for larger applications, it amortizes over the entire execution. All right. Yeah?
So is your system able to protect software from Meltdown, Spectre attacks?
No. So Meltdown and Spectre essentially changed the language level security guarantees, and so that is not something that we can defend against. More broadly, what I'm basically showing is that assuming that those let's say the specific parts of the program that are affected by security, as long as those can be isolated, you can inform the compiler as to how you can close side channels in the microarchitecture then. Okay. All right. So so as part of the future work, there are three. I mean, there is future work both in the area of side channels as well as outside of side channels. So earlier I told you about how we can use how we use super optimizers, but more broadly, given this function f, we essentially want to transform it into a new function, let's say f prime, which does not leak information through side channels, and it is still functionally equivalent. And a lot of this is similar to program synthesis or side channels, where you're given some specification in terms of inputs and outputs, or you're given some examples, and you're supposed to derive the code. And so there's a fair amount of literature that we can reuse from there. It's not directly applicable in the sense that we can't just take existing synthesis techniques and use them over here, because the microarchitectural specification is actually too big, so we have to worry about not just correctness but also security. But it's also that we also have to worry about proving properties, like we don't change the correctness of the program as a result of this transformation. So more broadly, when we're synthesizing from some sort of a microarchitectural specification down to the executable code for the compiler, we can have an intermediate layer like a domain-specific language and make that rich enough and do that so that we can analyze the program and see whether the specific transformation that we are generating composes well with complementary transformations that may be built in the compiler, so that these defenses are composable, or that it doesn't change the security or correctness guarantees of the program. And we can do that by analyzing types, by using solvers, and so But there's also the other part, which is how do we inform existence of side channels in these underlying layers up to the compiler? And right now, we do that using an ad hoc mix of program analysis, statistical techniques, and manual inspection as well. But going forward, one of my goals is to define more precise abstractions so that we can get better security guarantees. There's also the part on the other side, which is that right now, if you think about it, the only control that the compiler can express is in terms of the ISA. There's no direct control to either the microarchitecture or the physical hardware. And in that sense, the compiler is sort of at the mercy of the ISA. And so one potential avenue to pursue is how can we broaden the definition of the ISA to include not just the functional contract, but also the behavioral contract as well, as to what are the circumstances under which you want this particular execution to proceed. But there is, I mean, beyond all, behind all of this, there is a deeper underlying problem, which affects not just side channels, but security in general, and also performance and heterogeneity, which is that we have these layered design in terms of these abstractions, but oftentimes these layered designs actually become a liability. Like if you want to perform security debugging or performance debugging, for instance, oftentimes you require knowing a little bit about how the underlying implementation behaves. And on the other hand, using layered design actually explicitly prevents you from being able to peek into the implementation. And it affects a whole lot of other issues like energy optimizations or heterogeneity as well. And so perhaps one of the interesting ideas here is to be able to peek into the implementation or to analyze the underlying implementations, and especially do it at the hardware level, because that way we could discover these common security vulnerabilities, for instance. And our understanding of, sorry, did you have a question?
No.
Okay. Our understanding of program analysis in the software domain is fairly well developed to the extent that we can apply it to hardware design and how processors are actually developed to be able to recognize these sorts of opportunities. Now, we do have good semantics for the ISA. In a few years, perhaps we'll be able to analyze some complex portions of the code like the microarchitecture as well. But the part that is most interesting to me is the physical hardware. And I'm certainly not an expert on hardware design, but over the last few years, there have been some really interesting developments in that space. You feel, sorry.
So you made this, you said this sentence that, we're in a few years, we're going to actually be able to analyze the contract between the ISA and the microarchitecture.
Yeah.
Like, what makes you so optimistic?
On one hand, our static analysis techniques have been getting better. If you look at the way, if you look at the power of solvers, for instance, SMT solvers, we've been able to increase the scope of the applications that have been developed. At the same time, there have also been techniques to trade off the generality of the languages in which these programs are written, while in order to analyze bigger applications, like for instance the whole soundiness approach, where you limit the specific constructs which are used in the application and then analyze bigger applications as a result. So, I mean, if you look at the trend in terms of the kinds of applications that we've been able to analyze, we've been on the trajectory of analyzing bigger applications over time. Yeah.
Backing off that,
Yeah.
another problem, we presuppose the availability of the mapping from the instructions.
Yeah, absolutely, yes. And a lot of it depends on whether the microarchitecture is open source or not. But at the end of the day, I think perhaps a useful contribution that we can still make is showing an approach that this is possible. And then whoever has the right tools or right infrastructure can do it at their end. All right. But in the space of hardware design, over the last few years, there have been some really interesting developments. Like Chisel is one, but more broadly, there have been a lot of tools which talk about using functional programming languages for hardware design. And if we can port our understanding of program analysis, program verification, or transformation to the area of hardware design, we can we can sort of answer some of the bigger questions or harder questions like how do we quantify security, or how do we tune for energy optimization, or how do we deal with heterogeneity, given that we now understand both the details of the application that is being executed and the underlying platform in a much better manner. Okay. So if there is one particular final thought that I can leave you with, is that it is perhaps absolutely crucial that we look at least from the point of view of security, that we look at not just individual areas, but sort of how these interact across different parts of the whole computing stack. And so with that, I would like to thank my collaborators and sponsors, and also you for paying attention. And if you have any questions, I'll be happy to answer them. Yes. Yeah.
In your solution, in general, you have a 100% overhead potentially.
Potential.
Yeah.
Yeah.
There's a branch.
Oh yeah.
Normal code you execute one branch. In your case, you have to execute both.
Right.
Right. So then.
It's much more than 100%.
Yes. Potentially, I mean, the upper bound is actually way higher than just 100%.
Yeah, roughly.
Yeah.
That's what I'm saying. I mean,
Yeah.
There's no hope to go down below 100% in general, right? In that
Okay.
approach.
Right. Yeah.
And then in another scenario, the only thing I know that it's a side channel free, and the performance still doesn't get 100%.
Right.
The crypto code, right?
Yeah.
So they redesigned the crypto algorithm.
Yeah.
And
It is written in such a way.
My impression is the performance overhead is much less than 100%.
Oh yeah, absolutely. Yes.
So is it right that if you really want to solve this problem for general cases, you have to think about understanding the program and rewrite the program? There's some algorithm, AI algorithm is so smart.
Yeah.
Developer write a version, and that rewriter will just rewrite it mathematically so that it does the same thing, and it won't execute any redundant code, and it's a side channel free.
In a broad sense, that is what say translation validation or synthesis does, right? You're given some inputs, you're given some outputs, and you're supposed to derive code that matches that specification. And you can add these extra constraints where, in addition to matching the specification, these extra constraints say that you should not leak information through specific side channels. So there is perhaps hope in being able to leverage those ideas in order to use machine learning, for instance, to be able to generate code for those cases. But there's the orthogonal question as to what sort of performance overhead should we expect, whether it is either manually written or automatically generated. And that question is more along the lines, about how much security do we really care about? So if we want to eliminate side channels, then we need to make the side channel observations completely independent of the specific inputs that we're running. The sort of a related question to it is, can we do away with just checking, or can we do away with trading off so-called security and performance? Like for certain cases, we may care about making sure that there are no side channels at all. For certain other cases, we might be willing to give up some security. But that's sort of a very dangerous trajectory to go on, because first of all, what may seem as difficult for a human attacker may not be so difficult for a machine attacker, for instance. And secondly, it also depends on application to application. For one application, giving up some security might mean something which is completely different for a different application. And so right now, in the interest of conservative solutions, we're going ahead with a solution where we do not leak information at all, but there is hope for being able to understand the application semantics better and tailor our solutions to be able to give some level of security without making completely outrageous claims about how much security is being provided as part of the defense. Does that answer your question? Okay, sure.
I've got a variant to
Sure, yeah.
Mark's question.
Yeah.
Any of the benchmarks that you tested,
Uh-huh.
do you think that
Absolutely, yeah. So right now, for instance, our static analysis, which tries to identify which parts of the program need to be protected, it's basically a flow-sensitive, context-insensitive taint tracking. So if you had a human who would know that even though this function foo is called from two different places, I know that when it is called from the second instance, there is nothing that I need to worry about in this foo function. But when I call from this first instance, there is some security leakage over here. So being able to know those kinds of things, a deeper knowledge of the program can certainly help in terms of improving the performance. Now you could, for instance, duplicate this function and say that the second instance only call the second duplicated instance, which does not have any security provisions. So being a better understanding of the processor or better understanding of the program certainly can be helpful in reducing the performance overhead.
Can you describe your threat model?
Yes. Okay. Sorry. So there are different side channels that we're worried about, right? So for digital side channels, we're assuming that the adversary can measure any processor pins. So that includes the address trace, the control signals, and so on. As a result of that, the adversary can also use contention to observe, let's say, the cache behavior as well. So anything outside of registers is untrusted for our case. Now, the adversary could be an external entity. It could be a concurrently running application, or it could be an operating system as well.
So how do you load the memory into your registers?
So that is, so from the context of the hardware, there's only a move instruction. But in the program, we are trying to find out if that pointer that you are dereferencing to load from memory is secret or not. And we're transforming the program so that the pointer is never secret. So we can still use the load instruction to load from memory to into the registers, but we make sure that the location that you're accessing is not secret.
But the load instruction can take various amounts of time depending on where it's coming from.
Yes, but given that the address of the load instruction is independent of secret, the timing or any other properties, any other variable properties about the load instruction are also independent of the secrets then. So to give you an example, caches, for instance, take different amounts of time, right, based on whether it's a hit or a miss. But the hit or miss is dependent on the address. And so what we're saying is that instead of making all load instructions fixed latency, let's make sure that the address is independent of the secrets. And so your cache hits and misses can be completely independent of your secret values. And so, in fact, that gets to a bigger point that we can leverage existing optimizations like caches and prefetchers to our benefit instead of fighting them and turning them off.
So So are you just saying basically that certain portions of your programs are sensitive and others are not?
Yes. Yeah. So yeah, and it is the compiler's job to identify which portions of the program are secret and narrow down the focus to just those parts. Yeah.
Related to that, to recognize which part of the program can be sensitive, operates on sensitive input.
Right.
You do program analysis. You mentioned the flow sensitive.
Right.
So is it true that the program analysis accuracy depends on what language you use when you write the program?
It can certainly benefit.
Fundamentally, they are the same. I'm just saying, like, if I change my system into a functional language, would that make the analysis easier?
Absolutely. I definitely think. So the language has a huge part in being able to, or more importantly, when I say language, what I mean is how it gets translated into the LLVM IR. And having, not having undefined behavior, for instance, would make things simpler. Or being able to, prove more aggressively the properties about the underlying or properties about the code, and understanding how information flows back and forth certainly would make a difference. So there has been an effort out of UC San Diego where they've been designing a language for constant time programming. And it's not exactly a functional language, but it is trying to get rid of certain parts of C, for instance, which make it really hard to either write or analyze programs for constant time execution. And so certainly constraining the language down to specific features can certainly help.
They remove loops?
That's a very good point. I need to look back once again, but I think they might have made sure that loops can only execute in a bounded number of iterations. But yes, I mean loops, recursions are like the classic features which get in the way. Yeah.
So you do program transformations, right?
Yes.
So after you do transformation, do you verify that the
Transformation.
translated program behaves exactly the same as the transform?
So that is not something that we've done. We've not. Oh, sorry. I remembered that I had to repeat all the questions. I'm just realizing it. But yeah. So you can one approach is to verify if each of these transformations are completely valid. We started some effort on that front using Daphne. We didn't reach a certain completion just because other things took precedence. But we do care about correctness. In this case, the correctness is more of a verbal argument that we're not changing the functional behavior as we go along. But potentially a different approach, this goes back to ideas like synthesis, is that we can leverage the whole correct by construction approach, where you're synthesizing programs according to a series of transformations which are quote unquote are semantics preserving, and so those kinds of techniques can be used to ensure that your transform program will still be correct.
So what if the transform program does more than the original program? For example, if you transform a comparison to subtraction, right? Do you worry about integer overflows of that subtraction?
Yes, absolutely. Yeah. So, like I said, right now we haven't we don't have a formal model for correctness properties as such, and we haven't proved our transformations. But yes, so I mean. So one of the ways in which we derive that super optimization result for comparison to subtractions is by using GNU superopt, and it's generating results for was it PowerPC, and then we translate it to ARM. But I'm assuming that the super optimizer knows what are the constraints of these individual instructions, and then you can, while generating the results itself, you can make sure that it is generating results with respect to these constraints about potential overflows, and that it knows about it. Another approach that we slightly dabbled in is to expose the ISA semantics, like for ARM, for instance, to the Z3 solver. And it's sort of a dumb approach, but the idea is to generate random combinations of instructions, stitch together their semantics using the ISA definitions or the formal semantics of the ISA, and ask Z3 whether, hey, will the net result be the same as executing a certain, say, comparison operation? And that was too slow, but there are various ways to deal with correctness in this space, either after the fact or as part of the construction itself.
Let's thank Ashley.
Okay, thank you.